All right, welcome to the grasping session. We'll start with Jeffrey Mahler.
Hey, and thanks. I'm Jeff Mahler from UC Berkeley in the Auto Lab, and this is joint work with Florian here in the front row and my advisor, Ken Goldberg. And in this work, we use persistent homology, a technique from computational topology, to synthesize configurations of a robot gripper relative to an object that bound that object's motion under an energy field. For example, cupping an object under gravity or pushing an object in the plane. So there are many tasks that are still relatively easy and even tedious for humans to perform that are difficult for robots to perform. For example, pulling objects off shelves and packing into boxes. And one of the reasons this is challenging for robots is due to sensor noise, which can lead to uncertainty about the state of the world. For example, the shape and pose of objects. And my research and a lot of the research in our lab is focused around building robust manipulation primitives based on analytic methods that we can then fine-tune and update based on the outcomes of real trials. So for example, grasping and pushing objects. And one analytic method that we're particularly interested in considering this work is caging, which allows us to transport an object without completely immobilizing it. So formally, a cage is when an object shown here in blue cannot move arbitrarily far away from a set of obstacles shown in black without penetrating those objects. And in the configuration space, this means that the object's pose is in a bounded region of the free space. It's bounded by the collision space shown here in gray. And this offers robustness because all poses within that bounded region are still within the cage. However, complete caging may not always be necessary, for example, when forces such as gravity are present. And in work we presented at ICRA 2016 that appeared in RA Letters, we defined a new notion of energy-bounded cages. So given an energy field defined over pairs of poses, which could, for example, measure the work required to move an object from pose A to pose B, we define an energy-bounded cage as the following. A set of obstacles is a U energy-bounded cage of an object if the object can't move arbitrarily far away without going over a U threshold energy level. And in the configuration space, this means that it's in a bounded portion of the free space if you consider bounding by both the collision space and the super level set of poses above a certain energy level shown here in green. And we have similar robustness properties if the object's motion is indeed bounded below a certain energy level. There's also a natural way to quantify energy-bounded cages rather than just a 0-1. So we can find the minimum escape energy for an energy-bounded cage, which is the exact energy level at which the object is no longer able to escape the cage, and it sort of makes the largest region in configuration space around the configuration of interest. And in our ICRA 2016 work, we presented an algorithm for analyzing energy-bounded cages. So given a rigid configuration of a gripper relative to an object, can we estimate the minimum escape energy? And using weighted alpha shapes, we provided an algorithm. However, this algorithm took about 3 minutes to run per configuration. And this could be a hindrance to planning algorithms that, for example, need to search over many possible configurations to synthesize a grasp on the object. So in this work, we consider the problem of whether given just the object and a rigid configuration of obstacles and an energy field, can we synthesize a rank list of all energy-bounded cages on the object? And we do develop an algorithm for that in this work called Energy-Bounded Cage Synthesis 2D, which reports a list of verified energy-bounded cages using persistent homology. And we also can extend this to synthesize energy directions by discretizing and searching over energy directions. And we provide an application to constant velocity pushing in the plane. Now, our work builds off a lot of related work going back to the 90s, the first definitions of caging, and even to new theory on the problem. So actually, the talk after mine, you'll see some new results on three-finger caging. Our work in particular is inspired actually by techniques improving path non-existence and motion planning. And a particular algorithm that is mapping out the configuration space, trying to find and fill in a bunch of cells as being fully in collision or not in collision. And we also build off techniques for persistent homology for clustering motion plans for robots. So before I go in the algorithm, I want to note that our algorithm makes one additional assumption over analysis, which is that the energy field can be decomposed into this difference between a univariate potential over poses. And some examples of fields that satisfy this are gravity, where this difference is between the height of different configurations. And also, as we show in this paper in the supplemental file, we can lower bound the work required to push an object out of a constant velocity push from a gripper using this univariate potential here under constant velocity and quasi-static conditions. So before I go into the details, I just want to give an intuition of how this algorithm works and why we need this univariate potential. So I'm going to illustrate using the translational configuration space, but I also want to note that this algorithm works for x, y, and theta. You can put it into 3D by tiling across the rotation space. So first, note that the energy-bounded cages for this configuration might correspond to these wells here, these pockets in the space, but how to formalize that. We can sort all poses in the free space from highest to lowest potential, and then sweep and consider the super level sets of poses in the free space by energy level. And what we find is that there's critical points at which the connectivity of the free space changes, and it goes from being fully connected to one bounded region and one region outside, and there may actually be multiple of these. And as we continue to sweep to lower energy levels, these voids will also disappear in the configuration space. And the last poses to disappear before the void is closed off are actually the poses that are deepest in this well. So using the energy field restriction, we can actually estimate the energy of these energy-bounded cages by taking the difference in potential levels when the void was started and when it was ended. But there's some challenges to implementing this algorithm. First, how to represent the configuration space, which we use weighted alpha shapes for this, and also how do we find the bounded regions, and that's where persistent homology comes in. So our method for representing the configuration space, this is developed from work on path existence and motion planning. And in particular, what we do is we sample a bunch of poses uniformly in the workspace, and then for each pose in collision, we estimate a lower bound on the generalized penetration depth for that pose. So the minimum distance that we need to move that object to get it out of collision with the obstacles. And this corresponds to a ball lying strictly within the collision space in configuration space. And if we take many samples, we start to plot out this entire space. And after a while, we've got some representation of the interior of the collision space. Now, we've almost just made our problem harder at this point. We've got sort of a clump of frog eggs hanging out there in the collision space. But what we'd like to do is turn that into computational structure. And weighted alpha shapes are a tool to do this. So weighted alpha shapes will decompose a union of balls into a simplicial complex or a generalization of a graph. And the key property that this will preserve is that we'll be able to triangulate the convex hull of the points or centers of the balls while labeling which cells are strictly inside of the ball. So we'll know which cells are totally in collision. And here's an example of what this looks like when we discretize this configuration space. Then we can use persistent homology to look for the topological or connectivity changes in this space. And persistent homology works by first establishing a filtration over the space, which is a sorting over simplices, triangles, tetrahedra, edges in the simplicial complex by some function. And this function will use, in our work, we'll use the energy function. And as we sweep and continue to add simplices to the structure, we can mark the points at which something like a hole shows up and the point at which it disappears. And these will show up, these indices in the sorted list will show up as big off diagonals in what's called a persistence diagram. So these big off diagonals will correspond potentially to large energy bounded cages. And to walk through how this works for the example that we've been doing before, we first sort the simplices shown here in white from highest to lowest potential, and then we iteratively add them. So here we see a void is formed as an edge is added. Another void will be formed as the edge on the right is added. And later on, these voids will be completely closed off, and we'll see in the persistence diagram 2 large off diagonals. So to recap the entire algorithm, we were able to synthesize energy-bounded cages by sampling poses, constructing an alpha shape, running persistence, and finally checking the output for collisions in case we've undersampled the space. In our paper, we're able to show that this algorithm is correct in the sense that all energy-bounded cages it returns are truly energy-bounded cages. And without going into the details, the main intuition is that if we are able to keep the collision or forbidden space throughout this algorithm as a subset of the true forbidden space, for example, the y versus the true z here, and we find that the object is indeed still blocked off or bounded by this subset, then it is guaranteed to be bounded in the real space. We can also extend our algorithm to synthesizing pushes by first discretizing the configuration space and then resorting and reapplying the persistence algorithm for different push directions, for example. So in our experiments, we tried our algorithm on a number of challenging configurations across 4 grippers and 7 objects and 5 energy directions. And here are some examples of ranked energy-bounded cages found for parallel jaws. But I also wanted to hone in on a few of the more challenging examples of non-convex gripper geometry. So here we find on the left our Zymark 4 degree of freedom gripper. It finds this nice pairing of this boot-shaped object right into the width of the jaws. And another interesting example is in this Barrett hand, where, inspired by work from Sid Srinivasa's lab, where it actually finds a lateral push that's able to leverage this, this little hole or lip on the side of the object and cage it. Our algorithm's also able to prove complete cages, so before you do the energy sweep, persistent homology can actually find complete cages, and here's one example. We also looked at algorithm sensitivity to pose samples and runtime. We find that it converges in about 200,000 samples typically. And most exciting is that the runtime is very close to what it took to just analyze a single fixed configuration, about 200 seconds for every new input. And the reason for this is persistence is based on binary matrix operations, which are actually quite fast. We also ran experiments on a 4 degree of freedom Zymark robot, as you saw in the beginning. And here what it's trying to do is push linearly with constant velocity, push the object across a finish line. And in this task, it was successful 100% of the time versus about 40% for a random baseline. So dirty laundry. One of the big challenges with using this method or extending this method is that it may not scale well to higher dimensions. And one of the reasons is the computational complexity. So building these alpha shapes can scale exponentially in the dimensionality of the space. So you may need a supercomputer to, for example, do 6 degrees of freedom. Also, there are topological challenges, so moving to SO3, the way that space connects, it's not as straightforward to grid up the space computationally. There are also some numeric issues with the algorithm, so basically when the jaws are in contact and the object can sort of slide in contact with the object, small differences, say floating point 1e negative 5, could actually cause the algorithm to incorrectly close off this area in configuration space. And we're also working on integrating this into applications such as what we showed at the Waiver 2016 lab tours. We're particularly interested in using this to sort of push objects to the back of shelves and see what can be done with that. More info can be found at the website, and I'll take any questions. Thank you.
Thank you for the talk. I get to ask the first question because I'm actually the respondent too. So I had a question about quality of caging. We often analyze the grasp quality, but if my daughter is climbing around in the backseat of the car, she is caged by the car, but then I cannot drive until she is tightly caged in the car seat. Can you use these energy methods to sort of evaluate caging quality?
Right, so that was actually one of the motivators for us starting this work in the first place, was trying to evaluate cage quality. And I think it does depend a little bit on the application. So here, if you know about the strong presence of a force field such as gravity, it's useful. However, if your interest is in sort of restricting the object's motion as much as possible, like being strapped into a seat belt, maybe that's not the best metric. And in some cases, you may actually want the object to be as loosely caged as possible because that will be most robust to uncertainty. So I think there's a lot of work still to be done in this area. It's pretty exciting.
We'll take another question while Joel sets up. Okay, we got one here.
So one of the nice things about pushing is that it's relatively robust to uncertainty, and I was wondering whether you could somehow bound how poorly your pushes could be in terms of an uncertain pose of the gripper or the object.
Right, so we've thought about this a little bit on the theoretical side, and to do that, you might want to do something like look at, if I had a Gaussian pose uncertainty, how does the volume of that bounded region configuration space correspond to how much uncertainty I'm able to tolerate. At the same time, I think it can be difficult to analyze in general, so sampling-based methods could be very useful. And that's something that, for example, Sid Srinivasa's group has done a lot of work on. I think is relevant.
Okay, let's thank the speaker.